thank you so much. I'm just really honored to have been invited to give this talk and to share my research with you. So the topic of my talk is individual differences in navigation ability. And just to sort of get us thinking about this, I have a couple of questions I want to have you to think about. First of all, think about how good you think your sense of direction is, and we'll be talking about that. But also think about a time that you had to find your way to a new destination, for example, maybe a new restaurant in your town or city, or a new doctor's office or something. And think about which of the following might describe your strategy. Did you sort of know that it was like in the northeast part of the city and keep track of the direction that you were traveling? Were you more likely to ask for directions, telling you whether to turn right or left at particular streets or landmarks? Or did you just enter the destination into your GPS or sat nav and follow what it told you? So just that's just to get you thinking, and you know, we'll talk about these things later in the talk. I keep forgetting I can press next. So I'm interested in everyday navigation. So the sort of, you know, what the navigation abilities that we draw on in our everyday life. So for example, when you learn, maybe you got a new job and you have to learn the layout of the building where you're working, or maybe you traveled to a new city and, you know, for a vacation, not that we do that right now, but and had to, you know, learn the layout of that city so you could get to the places you want to visit. So that would be one important aspect. Another one is, you know, how well do we maintain a sense of, you know, our facing direction and our location while moving around in an environment. When you're navigating to somewhere, how well do you keep track of where you are in relation to where you started and your goal? And also things like planning, you know, a route to a goal location, or maybe even planning a route to accomplish, you know, an efficient route to accomplish a set of errands, maybe that you might have on Saturday or something like that. So these are all sort of everyday tasks that we do, and you know, and when we ask people how good is your sense of direction, we're really asking you kind of how well do you think you do these things compared to other people. Now, one thing I wanted to start by saying is that the sense of direction is not a sense as such. It actually depends on a lot of different cues and sources of information. So this is sort of an analysis of the many cues, representations, and computations that are involved in everyday navigation that I compiled with Thomas Bulbers in an article we wrote about 10 years ago. So, you know, when we're navigating, we're depending on a lot of different cues, sort of just environmental objects. So discrete landmarks in the environment, you know, maybe, you know, a bank or a mailbox or something. Global orientation cues, like maybe there's a mountain range that is always in the distance, you know, in a certain direction in your city or town. The structure, the geometric structure of the environment, just the shape of the environment is a cue. Symbolic representations such as maps, directions, linguistic directions that people gave you, or maybe your GPS. And then we also rely on sort of self-motion cues, cues that come from our body basically as we're moving, vestibular cues, motor efferents, proprioceptive, and even, you know, auditory cues in the environment, etc. Then, you know, navigation also includes on many different types of computation or mechanisms or processes like space perception, self-motion perception, and on executive processes such as, you know, selecting and maintaining our goals as we're navigating, or you know, road planning or selecting routes. And it depends on different types of representations in our minds. So, and we sort of divide those into online representations. So these are representations that you know, are active in your working memory while you're navigating. So again, your sense of where you are in the environment, you know, where your navigation goes, how far you are along your route, These are things that are online representations. And then there's also offline representations. So information that we would have stored maybe in our long-term memory, just memories of local views and what we had to do at that point in the environment, or what we call cognitive maps, or representations of the configuration of the environment. Also just networks of habitual routes. So really navigation is a very complex activity that depends on all of these things. What I want to talk about today, I want to talk about both, some of the methods we use to study navigation, and I'm focusing on behavioral methods. I sometimes collaborate with cognitive neuroscientists who we use fMRI, etc. But my main expertise and work is really based on behavioral studies. So we sometimes rely upon self-reports. We sometimes do studies of navigation in the real world. So we bring people out to, on our campus and ask them to point to things, just to get a sense of, for example, of how good of spatial representation they have of the environment. And then we sometimes do studies of navigation in virtual environments. And this can include both desktop environments where you're just navigating on a computer screen, but also immersive virtual environments where you literally walk in an environment and are surrounded by it. And I want to say that although I think there are many aspects of individual differences in navigation ability, most studies to date have focused on a particular sort of type of paradigm, which is one where basically we bring you to a new environment, give you a controlled amount of experience of that environment, maybe by taking routes or a set of routes through the environment, and then test how well you have learned the layout of that environment by things like having you point or have you try to take shortcuts in the environment. I think we need to broaden our methods, but those are the ones that are probably most used in the literature today. Okay, so I'll be focusing somewhat on those types of things. So the questions I'm going to address in my talk today then are first of all, how large are these differences between people? How different are we from each other? So that's the first question. Then, how valid is it to use self-reports? Is it really valid to just ask somebody, how good is your sense of direction? Does that tell us something meaningful? Third question is, can navigation ability be predicted by more traditional measures of spatial ability that we've had? Studying navigation abilities is fairly new, but we've had measures of spatial ability for over 100 years. And so can we predict navigation ability by some of these more traditional measures? I want to talk about how people differ in navigation strategies as well as ability, which is sort of a topic that my lab is really interested in right now. And finally, something we're just starting to study is, people are increasingly concerned that we're all relying too much on our GPS or sat-nav technologies, and is this hurting our natural spatial navigation abilities because we're basically not exercising them. So we'll start by the question of how large are ability differences between individuals. And I'm going to talk about two types of studies, one in the real world and one in virtual environments. So the first study was actually conducted by colleagues of mine at UCSB. Toru Ishikawa and Dan Montello was Toru's dissertation. And what they did was, and I'm going to use this whiteboard thing. What they did was they were actually interested in how people's representation of an environment improves or how it changes as they get more experience in the environment. But in fact, they're, one of the maybe more striking results of their study was just how big the individual differences were. So what they did was they drove people on two sort of novel routes in an area of Santa Barbara. It's sort of a very exclusive area that most college students don't go to. And this was one route, and then this is the second route. And for the first 4 weeks of the study, you were driven on these two routes once a week. And then on the fourth week, you they also drove you on this connecting route. And each week they tested people's knowledge of the layout of this environment by asking them to point, bringing them to different locations in the environment and asking them to point to other locations which were not visible from that point of view, estimate distances, and also sort of draw a map of the environment. Clear that. So, I'll turn this off now. So I'm just going to show you just a couple of the measures. So one of the measures was how well could people point to these landmarks in the environment. So this is sort of a measure of configural knowledge. If you really learned the configuration of the environment, you should be able to point to where things are in the environment. And the measure we use when we use of these direction estimates is angular error, which is the difference between where you pointed and where you should have pointed, right? Where the thing actually is. And that can, I mean, theoretically, that can range from 0 to 180. Because if you're, so there's, so if you're perfect, it's 0. If you're perfectly pointing in the opposite direction, it's 180. So if you're pointing randomly, it would average out at 90. So 90 is chance. And so what Toro and Dan found was that there were a few subjects, 4 of them out of 24, that were really accurate from the start, even from day 1. So these are 3 different, they're pointing either to each of the, within each of the routes and across the route. The axis is pointing from one route to the other. And so one group that were highly accurate, and they were like really had hardly any, I mean, their angular error was in only 30 degrees even on day 1, and got down to more like 20, which is about as good as you can be at something like this. Then there were people that, these 2 people that had poor navigation ability that really were at chance. They never, and they really didn't get better across the 10 weeks, the 10 exposures to this environment. And then there were people who were somewhere in the middle and improved, but interestingly, very few people showed a large improvement. Most, even if they improved, it was a very small improvement. But but basically the striking, and then another measure actually is even more striking. When they asked them to draw a map of the environment, you can see here that this most accurate person here, their map is almost a perfect map of the environment. This is the actual map on the left, whereas these other people, especially these 2, kind of got the idea there were 2 routes and a connector, but not much else. So and the way we measure how accurate a map is, we use something called bidimensional regression, which looks at the correspondence between the configuration of the landmarks as you drew them and how they actually were in the real environment. So this was a really important study in just showing just how big these differences are. But of course, it was very hard to do. I mean, Toro literally had to meet people on the UCSB campus, blindfold them and drive them to this location once a week for 10 weeks. So it was a huge effort. And an issue with doing a study like this is if somebody in some other part of the world wanted to do a similar study, they wouldn't be doing it in the same environment, right? So so one thing that has happened is that Nora Newcomb's lab has created a virtual environment version of this task. So their task is called Silkton. It's actually modeled on a college campus, and in their study again, you're in a virtual environment. It's a desktop virtual environment. You're led on 2 routes through 2 parts of the environment. You go back and forth, learn those a couple of times, and then you learn again a connecting route between the two environments. And again, the 2 main measures of this task are bringing people to different parts of the environment and have them basically turn the map to point where they think a different landmark is, and also to reconstruct the map. They just have all the landmarks and they get to put them on. They have to get to reconstruct the map. So they're similar to the measures, and they found a lot of the same results that Ishikawa and Montello found. Both large individual differences. In fact, they identified 3 types of people who could. They could point well within each of the routes, but not across the route. There was people that, could point well both within the routes and across the different routes, and people who really couldn't do either well. So they kind of found 3 different groups of people. And the nice thing about this task is that anybody in the world can download it and run it in their lab, and we're all running the same measure. So we don't have to worry about the fact of, like, is your environment similar to my environment? Just to sort of show you some of the individual differences, how big the individual differences are in this task. This is, my lab just started using it, and we've run 19 subjects to date. And so again, for pointing within each of those first 2 routes that you learned, you can see this is the median is around 20 degrees, which is really good. But there was somebody that was almost perfect, and then there was also an outlier that was at chance. And for pointing between the 2 routes, which is always less accurate, our mean was somewhere around 55 or something. And again, we have the full range, basically, from somebody who's almost perfect to somebody who's at chance. And similarly with our reconstruction scores, this when they reconstruct the configuration of the map, the measure there, as I say, is a measure based on bidimensional regression, and closer 1 means you're perfect. You almost reconstructed it perfectly. 0 means there's sort of no relationship with how you configure the landmarks and how they work. And you can see that people range from, again, we saw the whole range. So basically, it's clear that there really, at least based on these measures, that there really are large ability differences between individuals. And an interesting thing about this is that, most of these are with samples of college students. So at least in my lab, University of California students are like the top 10% of high school graduates from the States. So these are like, people that academically are really, really, the top 10%, but we're still seeing this huge range of ability of navigation ability. So the second question I wanted to address is, are self-reports of the sense of direction valid? So as we started, I asked you to think about how good your sense of direction is. And basically, if you haven't thought about that before, chances are that how you think you are, how good you think you are, is actually pretty accurate. So it seems that people know how good or bad they are. But I think another thing that's really notable about the sense of direction is people are willing to admit different levels of ability. So they're willing to, I've met lots of highly intelligent people, really distinguished people in their careers, that are happily tell me that they can't find their way out of a paper bag. So it's like there doesn't seem to be a stigma about being bad at this, which I think helps us with being able to actually, have a self-report measure. If you ask people how intelligent are you, they tend to overestimate their intelligence if they're lower and underestimate it if they're higher. So it's not a good measure. We do seem to know how good or bad we are, and we're willing to admit that. And this was first studied by Kozlowski and Bryant in 1977. So what Dan Montello and I did many years ago now, was we developed a scale that asks people not just how good is your sense of direction, but asks you about different everyday tasks where where a sense of direction might matter. And I'm always even though I developed the scale, I'm always a little skeptical about, well, how much should we be using self-report scales to measure an ability? And I always argue with Dan about this because he's a real proponent of this scale. And one point he made to me recently was, well, a really positive thing about this is it asks you about many different navigation experiences, and whereas a lab task, might only test one aspect of navigation ability. But we found that this was a reliable scale. It's internally consistent. People's responses to these different items are well correlated with each other. So it turns out to be it's turned out to be a useful scale. But the reason that it's useful is, for any scale like this, it has to, any self-report scale, we have to know that it's related to something that we can objectively measure to be sure, because maybe, people's self-reports of sense of direction, have nothing to do with reality, but in fact they do. So, so these are just some measures, some correlations that some of these came from the original standardized study that standardized this scale. We found that it was correlated 0.44 with people. Again, these are all error measures, so we're expecting negative correlations. Their ability to point to landmarks in a known environment, their ability to we brought some people, blindfolded them and brought them on a circuitous path, and then they had to point back to where they started. That was correlated with sense of direction. A number of studies have used this paradigm where you give people the experience of learning a new environment and then look at how well they've developed a representation of the configuration of that environment. And again, these find correlations in sort of the same range. The highest correlation reported that I know of was one by Jean Scholl, where she showed people photographs of an environment that was familiar to them. It was their college campus, and they had to look at the photograph and then turn their body to face the direction in the environment that the photographer had taken. And that was particularly highly correlated with the Santa Barbara sense of direction scale. So it's turned out to be a very useful scale, and it can be a really good way, for example, of just maybe if you're interested in, identifying people that either have a good or poor sense of direction for a study. It's fast. You can it takes 5 minutes to administer, and you can get a pretty good sense of how good a navigator people are. Interestingly, it's more highly correlated with personality than ability. So this is a study that I collaborated on with Bill Revell and David Utall labs at Northwestern, and they have a project. Revell's lab has a project where they're really developing, measures of general intelligence and various different abilities that can be, they can make available to researchers across the world. So in the context of this, there was one study where we were able to get data on the sense of direction scale and these measures for over 12,000 people. And what we found, and some of this had also echoes things that David Bryant had found years ago, we found that the sense of direction scale was correlated with 4 of the 5 personality measures and what's called the Big 5 personality scale: extroversion, conscientiousness, intellect or openness to experience, and emotional stability. And interestingly, it was not it was highly, maybe with 12,000, probably every correlation is significant, but it was only correlated 0.11 with general intelligence, and even less with mental rotation, which is most probably the most common measure of sort of spatial ability that's used in the literature. So, so that actually brings me to the next point of my talk, which is, can navigation ability be predicted by traditional measures of spatial ability? So the study of navigation abilities is relatively new, but we've had measures of spatial ability for a long time, for over 100 years. And again, one insight, thanks to my colleague, Dan Montello, had written an important paper in 1996 about different scales of space. And there are more scales than this, but we're going to talk just about these 2 scales. What we call the figural or small scale space, the space of small objects, things that you manipulate, things that they're sort of projectively smaller than the body. You sort of apprehend them by manipulating them. And basically the existing, almost all of the, at that point, when we started our study, which was published in 2006, almost all of the measures of spatial ability were at that scale. So these are sort of 2 typical ones: mental rotation or paper folding. In contrast, environmental or large-scale spatial ability involves spaces that are larger than the body that surround it, and that are, that we really apprehend by moving through an environment. There's an intermediate scale here called Vista scale, which I'm just not going to talk about today. That's sort of, what, like your view of a room, or it could be even your view of a city if you're on a mountain overlooking the city. So it's a view you can get in a single view. But we're particularly interested in, the scale that involves your ability to learn, just the type of environment that you think about moving through, and what you learn by moving through an environment where you can't see everything at a particular point. And interestingly, it's not necessarily just about size, because a small scale, a large scale, an environmental scale environment, the environment might include a building, whereas, as I say, you could have a vista maybe of looking down on a town or a mountain, which is larger. So it's really about how you engage with the space. And so several years ago now, we set out to see to what extent these sort of more figural or small scale spatial abilities, which are measured traditionally by spatial ability tests, and environmental or large scale spatial ability, to what extent are these related? And so we ran a big study. This was considered big back in the late 90s, over 200 students, and we gave them several measures of small scale, or what we might call object spatial ability, including the mental rotation test, an embedded figures test. So here for the mental rotation, if you don't know, you have to say which of the objects on the right could be the object on the left, but rotated in space. For embedded figures, you see a simple figure here, and you have to find that figure and kind of trace it in the figure on the left. And we also included a measure of spatial working memory, the arrow span task. And in that task, what you do is you see a sequence of arrows pointing to different locations in space, and then you have to sort of recreate that sequence. And you start off with maybe 2 arrows, and then you go up to 3, you go up to 4. And at some point, people break down, they can't do it anymore. And that's a measure of sort of their spatial working memory span. And then our measures of large-scale spatial ability were ability to learn the layout of a space with a controlled amount of experience to it and of that space. So we had people learn the layout of a real environment. This is a building on the UCSB campus that our subjects didn't go to very frequently, and they were walked through what floors of the building. Landmarks were pointed out to them, and then later we brought them back, and they were at each landmark, they had to point to something else, and they also had to draw a map of the environment, estimate distances. Then we also had them watch a video of a real environment. This is the Santa Barbara Courthouse, which is a beautiful building, and luckily most of our students had not been there. And so this one they learned by just watching a video that was taken by walking through the environment. And then they also learned the layout of very simple desktop virtual environments. And for each of these, we measured their ability to point to landmarks in the environment from different places, their ability to estimate distances to those landmarks, and then to draw a map showing the configuration of the environment and the landmarks. And just first of all, to sort of show you what these correlations were like. So again, a correlation of 0 means no relationship. A correlation of 1 means a perfect relationship. And everything was scaled. It was, I think, scored here. So we just manipulated all the variables so that all of the correlations would be positive. So even though some of these are actually error scores, so we just use the inverse of the error score or whatever. But what we see is that, these correlations, they're sort of, they're not super high. The highest one is 0.45. So they sort of range from, 0.08 to 0.45. I've bolded ones that are over 0.4, and, there were just 4 of these. I've sort of things that were below 0.2 are in gray. So you can see most of the correlations are more in the 0.2 to 0.3 range, which isn't super high. So it suggests that there's some relationship here, but it's not a perfect relationship. Now, one of the concerns when you look at correlations like this, let's say the correlation between pointing after learning from direct experience and embedded figures, when you see a correlation of 0.3, that could partly be a function of how well you've actually measured direct pointing and embedded figures. So each of these, you have to look at the sort of reliability of your measures of each of these things. Also, we're maybe not so much interested in how each of these variables relates to navigation ability, but how, like, if we a composite measure based on all of these three small scale abilities, how did they relate to navigation? So, I mean, without going into the technicalities of that, we ran what are called structural equation models to look at those relationships. So, so this measure here, this is a latent variable. This is kind of like a pure measure of small scale spatial ability, what these things kind of share, even when we factor out any reliability of measurement. And similarly, this is a measure of learning from direct experience, what these things share when we factor out unreliability. And now the path coefficient is 0.5, which means, maybe when you really look at the purest measures of these things, the correlation is about 0.5, which means they share about 25% of their variance. Now you can see that this small scale spatial ability has a much greater relationship when people learn from either a video or a virtual environment. And then we also included self-report sense of direction in this study, and that that added to the prediction of large scale spatial ability in both cases, but more so for learning from direct experience than learning from visual media. So in the basis of this, we basically argued that small and large scale spatial abilities are partially dissociated. So they are somewhat related to each other, but they're also dissociated. And that was also the conclusion of a recent study in Nature, I believe, by Mal Keeney et al. Now they really focused more on really arguing that they are, although they're dissociated, they're highly correlated, but their measures were measures from virtual environments, so they would have been maybe more like our learning from visual media type of measure. But I mean, I love their study, and it makes me want to do more work like this. And in fact, we have some new studies we're launching in our lab. So, so basically, you can't just perfectly predict somebody's navigation ability by giving them a set of mental rotation tests and things like that. These things are somewhat related, but also somewhat dissociated. Okay, so then the next thing I want to talk about is some studies we've been doing about, not just how people differ in navigation ability, but also in strategy. And so there are, again, people, self-report measures. Carol Lawton developed this as an important self-report measure back in 1994 that asked people about their strategy differences, how they navigate. And basically, it came down to there's sort of two major strategies that people use: an orientation strategy, so things like I kept track of the direction, north, south, east, and west in which I was going, or I kept track of the relationship between where I was and the center of town. So people who use this strategy seem to have a sense of, they really do seem to have a sense of the layout of the environment. And as they're navigating, they're thinking about where they are in relation to either cardinal directions or some maybe important salient part of the environment. And then there's also the other strategy that she identified was more route strategy, people who really seem to depend more on familiar routes. So before starting, I ask for directions, telling me whether to turn right or left at particular streets or landmarks. And one of the results that she found, one of the major results of her study was that men were more likely to report an orientation strategy and women were more likely to report a route strategy. So, so we wanted to look at this, but again, look at it in an objective measure of this rather than just a self-report. And we used a task that was developed by Marchetti, Baker, and Shelton. And in this task, basically what happens is the environment looks like this on the left. You learn the layout of a space by being brought on a tour of that space. In their case, by just watching a video that brings you to a tour of the space that takes this particular route. and in their study you were brought on that 9 times. And then after you have hopefully learned that route, they give you trials where they put you in one part of the environment and just ask you to navigate to another part. And what we're interested in is, do you navigate by taking the route that you learned, which is shown in blue here, or do you actually navigate by a shortcut? And the interesting thing about this work really relates to work with animals, and shows that these two strategies depend on different brain areas. So the strategy of taking a shortcut depends more on the hippocampus. So people who ended up using more of that strategy had more activation of the hippocampus while they were learning. The routler depends more on striatal systems, and people who use that strategy had more activation in striatum, caudate nucleus, etc., while they were learning. So, oops, I have to clear my thing here. And so what they find is that there's people who, mostly, I can turn off the whiteboard now, who mostly navigate by learned routes, right, which are over here on the left side of the distribution here. People who mostly navigate by shortcuts, and then a lot of people who actually are in the middle. And so they came up with this measure called the solution index, which is the number of times you used a shortcut over the number of times you successfully got to the goal location. So, so we were interested in it. So Alex Boone, a student in my lab, was interested in looking at this for other reasons. And so we developed our own version of this environment, of this virtual environment, but it basically had the same layout. And again, we had the same paradigm where people learn a particular route through an environment and then have to navigate from different locations. One of the things we found is that there were other strategies that people used besides the shortcut and the learned route. Some people actually reversed the learned route, and some people just sort of wandered and eventually found the goal. But we developed the same measure of number of shortcuts over a number of successful trials. And one of the things, again, we didn't go into this really with the intention of studying sex differences, but we found a very striking sex difference, that men were more likely to navigate by shortcuts. So, and this is in 2 different experiments. Men were more likely to navigate by shortcuts, whereas women were more likely to navigate by learned routes. And if you look at these heat maps over here, you can sort of see that men were more likely to navigate through the center of the maze, which wasn't on the path, whereas women were more likely to just follow the learned path. So, one question that comes up here is, well, is this because of an ability difference between men and women? I can talk more about ability differences. There is a small sex difference in favor of men on a lot of these navigation tasks, and where the men, so really to take a shortcut, you really have to have some sort of a measure of, not a perfect cognitive map, but you at least have created at least what we call graph knowledge. You have to have learned more than the route, right? You have to have learned something about, and maybe about how, where these things are, where these different locations are oriented in space in order to take a shortcut. So there's sort of a type of configural knowledge that's necessary to take a shortcut that you don't need to just take the learned route. So we were interested in whether, is that what's going on here? So we ran another study, and I think this is just one experiment of the study, where, and so because in the traditional measure, and this what's called this dual solution paradigm, the typical measure is to just ask people to just navigate in the test trials, just navigate to the goal location, but it doesn't say navigate efficiently or anything like that. So, so the question was, well, are people taking the learned route because they're not able to, or is it just their preference? And so we found that basically when we told people to take a shortcut, they were much more likely to take a shortcut. So what this indicates is that, even about both men and women, who maybe are able to take the shortcut don't always do so. And so people were much more likely to take the shortcut when they were told to do so. And again, you can sort of see that in the heat maps here on the right. But the sex difference still remained. It was a little bit reduced, but not significantly. And so even when they were told to take a shortcut, the men were more, and the men were still more likely to do it. I mean, they more likely to do it than the women. So now to just turn to some things we're looking at in the lab right now, which I can do pretty quickly. So one of the things I want to do with this task is generalize beyond desktop environments. I'm a little worried that some of this might be about familiarity with video game interfaces, because you have to use a video game interface in our task to learn the environment. We actually, in our task, you actually have to kind of navigate following arrows through the environment, and maybe men are more used to the video game controls so that they can devote more of their attention to learning at that learning phase. Another thing that I'm concerned about with this this environment is that in navigating in a virtual environment, there's no physical effort involved, or that might be saved by taking a shortcut. We've had some simulator sickness issues, especially when we did some work with older adults, which again I can go into in questions if you want. And then there is this thing that we found in our early individual differences measures that there seems to be some dissociation between learning in a real environment where you physically move, where you have all of your body-based cues like vestibular system and kinesthesis, versus learning from visual information alone. So one thing we're doing now is sort of developing different versions of this. In addition to our desktop version of this task, we now have an immersive virtual environment version of this task. We had to sort of scale down the environment so it would fit in our VR lab, but people literally walk now and learn the layout by walking. And we also had to add fog to the environment so they couldn't see the landmarks from if they weren't really close to them. And then we're also doing a similar task in a real environment, a place near actually our graduate student housing on campus, which has a sort of a layout similar to the original maze. And just really quickly, basically we had started these studies right before COVID. We're hoping Delta variant will allow us to run them, continue to run them this fall, getting geared up to do that. But basically, real quickly, just based on, I think, 10 subjects in each condition, we're seeing that maybe the difference between men and women is not as great if they physically walk in the environment than if they're learning from the virtual version of the same environment. And by the way, these are both the simplified environment. And in our study of outdoor navigation, where we again teach people about through an environment, and we're finding the same strategies that we found in the desktop environment. Some people are taking a shortcut if they're asked to start here and navigate to here. Some people take a shortcut. Some people take the route they learned. Some people reverse the route they learned, and some people again just wander and get there, although we stop them at some point if they can't get to it in a particular time. So this is work that I'm kind of excited about and hoping that we can continue once we get back into the lab this fall, which looks like it's going to happen. And the last thing I wanted to talk about is we're also starting to do some work on the question of whether GPS, sat-nav technologies are hurting our natural spatial abilities. This is something a lot of people are talking about. And just one way that we started to study it is by looking at the sort of characteristics of people that are more likely to use their GPS. So in a study that Carol published last year, we showed that we had a questionnaire that asked people how much they use their GPS. And basically, people who have a better sense of direction are less likely to use their GPS. So GPS use is, and these are fairly high correlations. Again, considering we haven't controlled for error of the measures, etc. people who use their GPS more tend to have more spatial anxiety and have a lower sense of direction. They also tend to be people who explore their environments more. Then Lexi Kunz, another student in my lab, she's looking, we decided, well, we shouldn't just look at GPS use in general, because there's different ways of using your GPS. And maybe, good navigators and poor navigators use GPS technologies differently. So good navigators maybe only use it for things like traffic estimates or time estimates to get to their place, which are things that, don't rely maybe on navigation ability. So they're kind of ways in which GPS augments our navigation abilities. And so she's finding this, people who just use it for every turn tend to be, again, lower sense of direction and higher spatial anxiety. And then the last thing we're doing is looking at cohort effects, because we figured that people 35 or older, learn to drive and navigate before GPS was in common use. And do they look different from younger adults? And they both depend on their GPS less, report less spatial anxiety, and sense of direction is correlated with use of GPS in younger adults, but not older adults. So those are just some emerging things that we're looking at in our lab. Of course, all of this is correlational, so we don't really know what the direction of causality is. So, so in summary then, what I talked about today is the fact that we do have large individual differences in navigation. Self-report, sense of direction are pretty predictive of those abilities, so they can be a useful measure. Navigation abilities are partially dissociated from small-scale spatial abilities. They include strategy differences, and use of GPS technologies may be affecting our navigation abilities. So I just want to end by thanking my main collaborators on this work, although there's many other people that have contributed across the years, and thank you for your attention, and I'm looking forward to your questions.